So now we're working with vertical stretch and vertical compression. And we're going to start off with the base function, f of x is equal to x squared. And just to remind you, 0, 0, 1, 1, negative 1, 1 are on that graph. And again, just to remind you, this is what the graph looks like just by a rough sketch. So 0, 0's on it, 1, 1's on it, negative 1, 1's on it. So what we're going to do is we're going to take some constant. I'm just going to take the number 2, and I'm going to multiply it by the function. And what that basically says is you're going to take 2 times x squared. So 0, 0 is still on the graph, but when we take 1, we plug that in. We're going to have 1 squared, which is 1 times 1, then multiplied by 2. So we get the ordered pair 1, 2. And we take negative 1 and we do the same thing. So negative 1 times negative 1 is 1, times 2 gets us 2. And if you look at the graph, 0, 0 is still on it, but now it's 1, 2, and negative 1, 2. So the graph is being lifted up twice as fast. The function is increasing 2 times as fast. Now, for a vertical compression, let's use an example of the absolute value of x. And again, the ordered pairs are 0, 0, 1, 1, negative 1, 1. And if you look at the graph, you get this sort of V shape going on, 0, 0, 1, 1, negative 1, 1. And we're going to take a number that's between 0 and 1, and we're going to multiply it by the function. And so we're going to take 1/2 times whatever value we got from the absolute value of x. So 0, 0 is still 0, 0, because 0 times 1/2 is still 0. But when we plug 1 in, we're going to have 1 and then 1/2, and then negative 1 and 1/2. And so notice I drew in the old y values when the x values were 1 and, typo, 1 and negative 1. But the new y values are 1/2. And so the graph gets flattened. I'll use the word flattened there. And so the phrase that we use, it's a vertical compression. Now, this is basically the idea. You take a constant, we're just going to call it the number a times f of x. It's going to be a stretch if a is greater than 1, and it's going to be a compression if it's between 0 and 1. Just a real quick comment. If a is negative, then what ends up happening is it flips the graph over the x-axis. Okay. Now, let's talk about horizontal stretch and horizontal compression. They kind of act sort of flip of the vertical stretch and vertical compression. And you have to do an adjustment to what's called the argument. You're not acting on the function, you're acting on the argument, and you're seeing, and let me just say the argument is the thing you're plugging in. So the x is the argument, okay? So here we're going to take the base function x squared again, but we're going to take 1/2 x, and we're going to see what the results are. Well, 1/2 x gets plugged in, and if you'll notice, that follows the rules of our composition of functions. So now we have 1/2 x getting squared. Well, 1/2 times 1/2 is 1/4, and x times x is x squared. So if we take 0 and we plug it in, we've got 0 squared, and 0 times a quarter is still just 0. Take the 1, plug it in, and you're going to get 1/4 out. Take negative 1, plug it in, and you're also going to get 1/4 out. And so what ends up happening is the height of the graph. The height of the graph gets lowered, but visually it looks like the graph is getting pulled because it's growing slower. It's getting pulled wider, and so it's called a horizontal stretch. All right, let me do a real quick sketch of this just to show you what I mean. So we had 0, 0, we had 1, 1, and we had negative 1, 1. And this was our old graph, okay? Well, now it's 0, 0, it's 1 1/4. It's negative 1 1/4. And so if you visualize like a hand right here and a hand right here pulling in that direction and that direction. It's getting horizontally stretched, okay? So notice the size of the multiplier on the argument, okay? Now, we're going to take f of x and we're going to put in a number that's larger than 1. And so what ends up happening is we have this 2x squared, so now it's 4x squared. 2 squared, x squared. So the ordered pair 0, 0 stays 0, 0, but the ordered, or the x value for 1 now goes to 4. And the negative 1 goes to 4. And so at 1 and negative 1 back up here, we're way up at 4. And if I graph that from the horizontal perspective, it's getting pushed in. And so from the horizontal perspective, it's getting compressed. So like it's getting squeezed that way. So if the argument that we, when we're looking at the argument and we get a multiplier that's over 1 or less than negative 1, and I have to make a comment there, what you're getting is the compression. If it's between negative 1 and 1, that's when you're getting your horizontal stretch. Now, again, I have to be a little cautious here. If it's negative, if the value is negative, what ends up occurring, and I need you to see this, and then I got to be quick about this because I'm running out of time. So I'm using the square root of x as the base function for this. And the domain is x is greater than or equal to 0. Well, the old graph would look like this. But suppose our multiplier is a negative. Well, in order for us to think about the fact that this has to work, our x values need to be smaller than 0 or 0. And the reason is a negative times a negative is a positive. Then we can take the square root. So we actually have to take values on this side. And so the graph actually exists on the left-hand side. And so if we take our values, if we take 0 and we plug it in, we still get 0, 0. But I've got to take an x value of negative 1/4. X value of negative 1/4, and I plug it in here. And so what I'm going to have is the square root of negative 4 times negative 1/4. Well, the negative times the negative becomes a positive, and the 4 will go into 4 one time, so I'm left with the square root of 1, which is 1. So this ordered pair is negative 1/4, 1. If I take negative 1 and plug it in, I have the square root of 4 times negative 1, which is just the square root of positive 4, which is now 2. So at negative 1, I get the y value 2. So the graph gets flipped if what we're putting in the argument is negative, okay? Flipped over the y-axis. Okay, time's running out, so I gotta let you go.